Our project was the Venus flytrap. I'm Calen.
And I'm Greg Giebel.
How does a Venus flytrap behave? There are three main concepts that a Venus flytrap follows that we wanted to mimic in our project. The first is that anything that goes inside the organism, the Venus flytrap, it will close its mouth on. The second is that once it goes in, depending on if it's a living organism, it will stay shut. And if it is not a living organism, it'll let it go. So this is the main three things again that we wanted to mimic. So to detect the entering of the mouth, the way that we wanted to do that was using a photodiode and an IR LED. So once this was broken, we could detect, oh, something's entered the mouth, we should close on it. The second thing to detect whether it's a living object was we wanted to use a photoresistor. So depending on the color, that's the way that we detected if it was living or not. We would either stay shut or open back up. And we used two motors connected to different gear systems to get this accomplished. So these are a few pictures of our setup for the experiment, or the lab, I guess I should say. Here you see the photodiode and IR LED setup, which again was closing the mouth. Here we just have a side view of everything, so you can see we have our little Arduino and breadboards up here, another breadboard down here, and then our whole setup. So again, our Venus flytrap was inside a box, as you can see, so that most of the light was taken away. So more close-ups, you can see the blue LED and the photoresistors in there. Here's a little closer picture with the mouth, and the motors are hidden under this piece of cardboard. This is our circuit for our photodiode. We had a 5-volt connected to a resistor, which in our case was 75 ohm, connected to IR LED. And then away from that, on the other side of the gap, which is where the object fell through, we had the photodiode, which could detect the IR LED and the Arduino, so that we could, program and give some logic behind closing the mouth. Here's a photoresistor schematic. Again, it's very similar to the one that we just showed. The things that are replaced are photoresistor and blue LED instead of photodiode and IR LED. And again, the Arduino was connected to the photoresistor to measure different voltages. And then this is the most complex probably of all of our circuits. It's the motor control. So as you can see, we had 5 volts connected to a NPN transistor and a negative 5 volts connected to a PNP transistor. And depending on if we wanted it to open or close, we would send different, either 3.3 volts or 0 volt to this sort of wire right here from the Arduino, and that would close one and open the other depending. So again, an NPN transistor will close if there is current to the base, and then the PNP will close if there is no current. So if you were to give 3.3 volts, the NPN side of the switch would close, and if you were to give 0, the PNP side would close. And depending on that, it would run these motors in opposite directions. And again, the motor orientation was the same electrically, but physically they were flipped so that they turn opposite directions.
So we ran into a series of design hurdles while creating this project, the first of which was the motor torque. The initial solution of ours was to use a single motor and have the gears on opposite sides of it so it would spin in 2 different directions. But this did not generate enough torque to actually move both of the pieces of the mouth. So we had to put it onto separate motors and use a series of gears to actually generate the necessary torque. Also, once we did this, motor speed became an issue because our 2 motors did not run at the same rate. Even when given the same voltage and hooked up in parallel, one of the 2 motors had its interior axle loose and spinning, and the other one did not. The one that had it loose and spinning was wasting energy and ran slower. And the final hurdle we ran into was color sensing consistency. In that photoresistor circuit, we were able to tell whether something was blue or not in a controlled environment outside of our box. But once we put it into the box, there were too many factors for us to control at once, such as the shadow of a person leaning over the box to drop in an object, the distance the object fell from the actual LED and resistor, and the reflective surface of the object that when it fell in. A crumpled up ball of paper had far too variant surface. So in the end, most of our things were successes. The sensing of an object falling in worked almost immediately. We only occasionally had to reposition it to make sure that the two pieces were still in line. The moving of the motors, we solved the issue of the two running at different speeds by simply having one motor do more work than the other and not positioning the two pieces of the mouth at the same height as a result. But we did have a failure in that we were never able to get the color sensing to actually work inside of the project. So we had to scrap that part. And if we were to do this again, our first thing to do would be to fix the color fixing. We had a few possible ideas, such as making a large object with a uniform surface, such as a wedge, that would occupy the entire mouth, so there would be a uniform distance from the resistor, or from the LED and photoresistor. And the other option was to put the LED and the photoresistor on opposite sides of the box, or of the mouth, and use transparent blue paper as the object to drop through. If the light passed through it, the paper was blue. If the light did not pass through it, it was a transparent paper of a different color, and we would be able to tell whether or not the object was edible. That's all. Thank you for listening.